all on the same page now? So we're going to go color by color.
You know, it doesn't affect it if you just...
Blue! If you had blue dice, how does this look with your distribution?
Yeah.
Look about right? Look what you guys got? Yes? I got an average of about 8.17. Standard deviation of 2.65.
Sure.
Good. Please, Sandy.
It's been too long, I'm sorry. So the
Oh.
circle like that.
This is...
What about the one above it?
This is... Your TI calls it X bar.
No, there's an SX.
Yes. Oh, you mean this guy.
That was standard deviation.
That's standard deviation.
On ours, it's 2.69, and the 2.65 is the...
Yes, and that's what that guy is. That's sigma. Remember, now time out. These guys are asking a very good question.
Oh.
These guys are asking a very good question. This is where you can't become a slave to your machine. And I thank you guys for asking this because you're not becoming that. There are two standard deviations listed on your TI. One is a sample and one is a population. Why are we using the population standard deviation?
Because we have the whole...
Because you guys actually counted every single element of the population, didn't you?
And a sample would be taken from ours.
And hold tight in about 20 minutes, that's what we're going to be doing. Sampling from this.
Okay.
But yes, so that explains why you're ignoring the SX. Just like we've been doing with the binomial and so forth as we've been going through. We only look at the sigma because you guys actually counted every single element of your population, all 36 of them, right? There are 36 elements in your population and you counted every single one. So that's why there's no uncertainty. There's no sample being drawn. Cool? Now, and that was a good question, thank you guys for that. Also, you won't see the Greek letter mu in your TIs, which kind of frustrates me, honestly, to be perfectly honest with you. I don't like the fact that mu's not there. X bar is the sample average. The reason TI does not give you mu is kind of a lame one. The calculation for mu and X bar are exactly the same. Add everything up and divide by how many you got. The calculation for the two different standard deviations are actually a smidge different. And that's why they give you two. I don't like the fact that they don't give you a mu and an X bar, but they don't. Sorry. No, it's okay. I guess Meryl does. But it's okay. It's totally fine. So fair enough? So I call this a skewed distribution. Skewed left, if you will. Skewed left because there's a hump over here and a tail over here. So notice where the average is. The average is 8.17. The lion's share of the data is over here. 8.17 is kind of to the left of that hump a little bit. And that's why it's called skewed left. So just keep that in the back of your mind. And I mean the back of your mind right now. We'll come back to that. My yellows, does this agree with yours? Yes? This is skewed to the right because you've got this and then kind of a run out tail there. Yeah, I got an average of 4.5. Does that agree with what you guys got? An average of 4.5? Okay, good. Notice the highest point is at 3, 4.5's over here. It's skewed. The average is pulled that way because of that crazy tail out there. I got a 2.22 sigma. Is that yellow 2.22 sound right for your sigma? Ish, we're getting there. Okay, good. We'll come back to that too. There is a bit of fiction we are participating in here. What bit of fiction are we participating in here? Hold that thought. Green. This is the flipping the bird distribution. I like this one. The way I made these up. The way I made these up. This is how much of a geek I am. What I did was, I created random numbers between 1 and 6. And then in here, this little block here is the actual sums that you guys calculated. And then I just kept pressing F9 till something looked interesting to me. So I just kept doing like this until something was like, oh, that's kind of cool. And then I built those dice. So when I saw the flipping the bird one, I'm like, oh, that's kind of cool. I'll build that one. And when I saw the goofy skewed ones, I mean, notice how they're all kind of skewed, right? Like that one looks kind of like the yellow ones. For some reason, I got the yellow one first. Whoops. So let's just keep going real quick here. There's another skewed. Oh, that's kind of a fun one. That one actually looks kind of like the orange dice. Those of you that had orange dice, that's similar. Very good, very good. That's a nice little fun little sub hump over there on the side. So anyway, this is another use of Excel that you probably didn't think, oh, look at that one. Oh, that's kind of cool, except it's almost perfectly waved, except for that. It's almost perfectly symmetric. I love open up. I'm going to take that one and put it over here anyway. Let me stop, because this is how I get sidetracked. So anyway, you guys got an average of 7? A plus or minus 2.92? Now notice, this one has the same average as fair dice, 7. And hopefully you can see why. It's symmetric, just like the fair dice. But the difference is it's not symmetric like this. It's symmetric, and it's got a lot of weight on the right and a lot of weight on the left. And that's why sigma's bigger. It's got a bigger plus or minus because there's more stuff away from 7. More stuff farther away makes for a larger value of that standard deviation. Kind of rad, huh? I was actually trying to build one in Excel that went like this. Explain to me why I can't. I sat there for about 5 minutes with my hand down on F9 trying to figure out how to get a U-shaped distribution.
Because the most common, like, number combinations is right around 7. So
But that's on fair dice. Remember, I'm messing with the dice.
Yeah.
What's your new... You have more ways of combining to get that number.
What if I have the choice about what goes where, though?
Well, to get low dice, you have to have low numbers, like all low numbers, and if you want high ones, you have to have all
See, what
high
you're saying, Riley, is true, but Kale's got it. So check this out. If I needed a lot of 2s and a lot of 12s, to make 2, what do you need? You need 1s on one die and a 1 on the other die. At least a couple of them, right? And to get 12s, you need to have a 6 and a 6. Now, I'm keeping myself to the rule. I don't want anything higher than a 6 or anything lower than a 1.
But if you add those together, you get a 7.
And that was the problem. Even if I put a die full of 1s and a die full of 6s, right, which wouldn't work because I couldn't get 12s or 2s that way, but 3 and 3 and 3 and 3, I'm still going to have a buttload of 7 possibilities with the 1s and the 6s falling together, right? So the best I could do is something along these lines. So Riley, even with the dice not fixed, I was still having a problem getting that U shape. So this is as close as I can get, which I thought was kind of fun. Cool? Thank you. All right. Orange. Look like your guys? I like this one. It was bimodal. You got 2 spikes, which are kind of fun. The average is 7, which ends up being right about here. Plus or minus 2.15. Does that agree with you guys? 2.15. Awesome. And red. This was the only one that still looked like a bell curve. The only one that still looked like a bell curve. So it's tighter. Now, your guys' numbers on your dice were a lot larger than on, say, the orange dice or the yellow dice. You guys had a lot of 6s and 5s, I remember correctly. The green dice, oops, you guys that had green, you guys were the only ones where both dice matched. Both of your dice were exactly the same. Whatever was on one was on the other. Everybody else's dice were different from one die to the other. And again, that was not because I planned it that way. That's because Excel just randomly gave me those values. I'm like, that looks like fun. Let's make that one. So, fair enough? So here's the red. I got an average of 9.17-ish, somewhere in there with you guys. Plus or minus 1.46. Look how small that is compared to the other ones. Why is that one so small? The other ones were all 2-point-somethings. Why is this so small? Andrea?
Because that one's tighter than that.
Smushes in, yes? It's all smushed together. Nothing smaller than 6.
So that one's less skewed then?
It's less skewed because it's more symmetric. Nothing's less skewed than this one.
But it varies less from...
I mean, that one's perfectly symmetric. Here's the deal. I'm being a bit of a bastard. I'm being a bit of a bastard on you. The word skew in statistics, the pure definition of skew, is deviation from symmetry. We've been using it conversationally as deviation from a bell curve. But bell curves aren't the only kind of curves that are symmetric, are they? There are other graphs that are symmetric. For example, this one. This one's perfectly symmetric. If you fold it down the middle, it looks the same left and right-hand side. So, skew generally means it's not symmetric. Not that it's not bell-shaped, although we've been using them interchangeably, and that's okay. There's nothing wrong with that, because most of the time you guys encounter bell shapes. You're about to see one more reason why you see it all the time, as we go through the back part of this experiment. There's something behind me. So, Eric, ask me that question again.
No.
No, okay. I refuse to, that's okay. Now, here's the problem. These five distributions represent populations. Granted, they're a pair of dice. Just like when you go to Vegas and play, like when 105 played craps earlier today. They had a pair of dice in their hands. But here's the deal. When you do statistics, how often do you get to count your population?
Not very often.
Not very. As a matter of fact, the few times you can count your populations are either when the population is very small, and you can actually get out and do a census of them, which again, does not happen very often. Or if you're doing something like gambling in Vegas, when you can actually count the cards or count the outcomes on the dice. Generally speaking, what do you have to do? You've got to take a sample, right? So what we just did was, in a sense, fiction. We counted your entire population. What we're going to do now is We're going to redo the experiment. Suppose, for example, I'm interested in the average of the red dice. Now, realistically speaking, there's no way you could go out and count all the red dice outcomes and average them together to get 9.17, could you? There's no way you could do that. You're not allowed to, because it's too big. Imagine that the red dice were the number of children with ADHD in America. You can't count them all. While we're sitting here talking, one more's been born, one more's not a child anymore. The population's constantly shifting. So what do? You take a sample of them. You draw a sample of them. That's what you guys are going to do next for the in-class quiz. You're actually going to do statistics, not parameters. These are parameters, yes? These are parameters. You're about to do statistics and not parameters. So you're going to be rolling your dice exactly and looking for the sample averages and the sample standard deviations that you get. So this is all, I'm going to shut this down, we don't get this right now. This is all on the in-class quiz.